Okay, just about time to get going. Some people may watch the start of these things. I got the test graded, and right after class, I'm going to be emailing those out to you. I wasn't able to grade them online because I had a variety of, some students emailed them to me and some turned them in there. So I just had to sort of work with, download them all to my computer and grade them there. But I'll be posting those or emailing those to each individual student here. Yeah, as soon as class is done today. So for today, we're going to be continuing on with some conservation of mechanical energy problems, looking at a different type of potential energy, and then maybe looking at one where energy is not conserved, where it gets stolen from the system. So, and we'll do a few more problems like that tomorrow. Okay, so we should be in the visualizer, and I think I figured out how to make it, maybe. Well, let's see. I thought if I clicked over in this column that everything disappeared, but now it's just going crazy. Okay, just have to be patient. Okay, just for a quick review before I do anything else, we've been dealing with mechanical energy and sometimes dealing with work, but the mechanical energy shows up as either kinetic energy, Ke, which is the 1/2 mv squared, and that's pretty much the only kind of mechanical energy we're going to have for the motion, but it's also, for us, it's been gravitational potential energy. And that, the expression that we're using for that is just mgh, where h is the height above some reference point, and we get to pick where that reference point is. Turns out that with both of these types of energies, it's the differences in energy that end up mattering, particularly with gravitational potential energy. And so the difference in gravitational potential energy between 2 points for lifting some mass or something like that is just going to be mgh, where the amount up here will be mgh higher than the amount down there. And it doesn't matter if you choose to call this point up here where GPE, PE is equal to 0. If that's the case, then you would describe this to have a gravitational potential energy of minus mgh. And still, this one is mgh higher than that one. And so you can pick that 0 point anywhere you want, but usually we pick it at the lowest point in the problem. So it is where it happens to be 0. So those are the things. But what we find out is that the, total mechanical energy and I'll put this in parentheses, initial, will equal, and I'm going to abbreviate this, it's TME now, TME final. And so that's what we use when we're applying conservation of energy principles to these problems. Now, the last problem we'll do today, we'll actually look at a situation where we have friction, and friction will steal mechanical energy from the system. And in that case, the final total mechanical energy ends up being less than the initial by the amount of work done by friction. And so we'll see how to deal with that when we come to it. All right, but this one I thought was kind of an interesting problem. In a downhill ski race, surprisingly little advantage is gained by getting a running start. And the reason is that the initial kinetic energy is small compared with the gain in gravitational potential energy, even on small hills. So to demonstrate this, find the final speed and the time taken for a skier who skis 70 meters along a 30-degree slope, neglecting friction. Okay, this ought to be fun. So we'll imagine this is our slope here. And, well, actually, I'll just draw an angle with the horizontal here. I'm pretty sure this is the one that they mean to be 30 degrees. And I'm going to write this as 30.0 degrees. I probably copied this directly out of the book as it was, but that's only one significant figure when it's written as 30 degrees. So, all righty. Well, let's see. We'll have an H here that that'll be the skier's initial height above their stopping point. The 70 meters is the distance down the slope. So H divided by 70 meters would equal the sine of 30 degrees. .0 degrees, and the sine of 30 degrees I happen to have memorized because I took trigonometry in the olden days when for particular angle values you memorized it. Sine of 30 degrees is 1/2. So H is going to end up equaling 35.0 meters. And if you plug in, multiply out from underneath by 70, you go on 70 times sine 30, you get 35 meters. So just in case you don't have that memorized. But anyway, that's what the height is. And initially, we would have, or for part A on here, if they start from rest, we'd have their total mechanical energy at that time is just going to be mgh. Their kinetic energy is 0. And so I'm going to have this as GPE and let's see, kinetic energy. And that'll equal their final total mechanical energy. Well, when they get down to here, they don't have any gravitational potential energy anymore. I chose this to be the height where gravitational potential energy is equal to 0. So they would have 0 for the gravitational potential energy, and then they would have kinetic energy down there. So plus 1/2 mv squared. And we can figure out how fast they're going to be going at the bottom. All right, well, set these two things equal to each other. The first thing I would do is divide out the mass, because both expressions have one, so I'd end up with GH is equal to 1/2 v squared, multiply both sides by 2, and I get 2GH equals v squared, or v is equal to the square root of 2GH. So that final speed down there at the bottom, two times 9.81 times the 35.0 meters. And I get that their final speed is 26.2 meters per second. Okay, let's see. What else am I supposed to figure out? Find the final speed, got that, and the time taken for a skier who skis 70 meters along a 30-degree slope. Okay, well, if they're going down a hill like this, I want to know the total time taken. I'm probably going to have to use my Newton's law stuff a little bit. So I'll grab a piece of paper, scratch paper, and do that. Sometimes you'll be asked questions that you can't solve completely just by looking at energy considerations. Although they have constant acceleration, we can be a little smarter. Okay, when you have constant acceleration, okay, if you make a graph of v versus t for some interval, this would be starting at rest, and it's going to be a straight line when you have constant acceleration, and the average velocity, the average, is equal to 1/2 of the initial plus the final. So V average is going to be V naught plus, I'll call this V final, plus V final, whoops, that was T on the axis, it's not part of this equation, divided by 2. Well, V naught is equal to 0, and so in this case, I'll have that V average is just going to be 1/2 V final, or it's going to be 13.1 meters per second. And the distance traveled, which I can let x be down the plane, the distance, the 70.0, I forgot the 0.0 on that one, is going to equal V average times t, but V average is just half of that. So the t that it takes is going to be 70.0 meters divided by V average, which is half of that, 13.1 meters per second. So 70 divided by is going to be 5.34 seconds. Okay, so I have that. And now that's just when they don't get a running start. So now let's imagine that somehow the skier, maybe there was a flat part up here and they got going up to 2.5 meters per second and then started their downhill descent there. And we'll see what we can do with that. I'm going to need more scratch paper here. Good, this one's blank on both sides. So for part B, again, I'll have the gravitational potential energy plus the kinetic energy is going to equal, this is initial, this is final. And so gravitational potential energy plus kinetic energy. Okay, well, the gravitational potential energy is still mgh at the start, and it's still 0 at the end. But in this case, I've got some initial kinetic energy. In the first example, I didn't, but here I'll have 1/2 m v initial squared, and then over here I'll have 1/2 m v final squared. Okay. Now again, mass, 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 every term has the mass, so I can get rid of that, but I'll have gh is equal to 1/2 v initial, whoops, no, plus 1/2 v initial squared is equal to 1/2 v final squared. So doing that, multiply both sides by 2, and I'll get 2gh plus v initial squared is going to equal v final squared. Or I take the square root of both sides, and I would have 2gh plus v initial squared equals v final squared, which is going to equal the square root of 2 times 9.81 meters per second squared times h, which was 35.0 meters. I'm running out of room. I'll do this. Whoops, that's v final now. V final is going to equal, rewrite that, 2 times 9.81 meters per second squared times 35.0 meters plus V initial, which was just 2.50 meters per second squared. Now, just kind of thinking about it, 2 times 35 is going to be 70. 70 times this is going to be around 700. And when I square 2.5, I think that's 6 1/4. So 6 1/4 compared to 700 is not all that big, but let's see how much of a difference it makes on the final velocity. Let's see, 2 times. Okay, and I need to take the square root of that. I get 26.3 meters per second is what the final speed is. I had 26.2 the first time, so it's actually, the first time I had, where is it? Yeah, I had 26.20. This time I get 26.32. So really not, it's just 1/10 of a meter per second difference as far as the speed. Now, what about the elapsed time for their trip? Well, let's see. I can still do a velocity averaging thing here. If I, is this showing? Yeah, I think it is. I still have a constant acceleration downward. In fact, the acceleration ends up being g sine theta. But now my average velocity will still be the average of the initial and the final. So VAVG is going to be 26.3 meters per second plus 2.50 meters per second divided by 2. And V average is going to equal, oh shoot, that was not what I wanted. Okay, for the average velocity, I get 14.4 meters per second. Yeah, I guess that makes sense. And so the elapsed time would equal the 70 meters divided by the 14.4 meters per second. I get 4.86 seconds. Actually, that's somewhat significant, the time, because in the ski races, sometimes people will win by a few hundredths of a second, but the speed at the bottom was not that much greater, but the average speed was a little bit higher, or enough higher to matter, although they do not have just 70-meter races, and they're not just straight down a hill either, so that's not going to be all that big. But a little bit of advantage would be gained by getting a running start, except you'd, with television cameras on you, I don't think you could get away with it. So, all righty. Well, another conservation of energy thing, but we had to pull in some stuff from our old average velocity things, which was probably good to do. A couple of weeks, we've got a final test coming up, and you might want to have to be thinking about some of those things. Okay, here's an Atwood's machine, a different way of approaching it. And we have a system of 2 paint buckets connected by a lightweight rope passing over a pulley. It's released from rest with a 12-gallon or 12-kilogram bucket 2 meters above the floor. So this distance here is going to be 2.00 meters. Use the principle of conservation of energy to find the speed with which the bucket strikes the floor and neglect friction and inertia in the pulley. Something else we could do is calculate the acceleration of this. And this would be a different way of getting the acceleration. We developed an expression for that Atwood's machine lab that we did, but it involved some forces and tensions and things like that. But let's see how it will work out in this case. I'm going to call this mass here M sub H. It's the heavier of the two. And this one here, M sub L. And I'll have the initial and the final in this case. And here I'll just call this 2 meters H. So get that. Well, for starting with, what I have is no kinetic energy. All I have is the gravitational potential energy of that bucket. And I'm going to call the low spot where the gravitational potential energy is equal to 0, right when that bucket hits the floor. So initially, I just have M sub H, GH is the initial energy that I have. Now at the end, this will have dropped down to the floor, so it no longer has gravitational potential energy, but this will have risen by the same amount. And so I'll have M sub L GH for gravitational potential energy, but both masses will be moving. I'm interested in the instant when this mass has not yet struck the floor. So we can assume that it's 1/1,000,000th of a millimeter above the floor and not being slowed down yet. Essentially, it's at the floor, and its height, it's lost all its gravitational potential energy. But I will have, 1/2 M sub L V squared plus 1/2 M sub H V squared. They're tied together by a cord, so they're moving at the same speed. And so that's what I have for the total final energy. I have the gravitational potential energy of this lighter mass that rose up. And then I've got the kinetic energy of the two masses. They're both moving together there. And so I have that. Now, I can do a little bit of work here and solve for that final speed And let's see, if I subtract mlgh from both sides, so I'll have mh, let's see, gh minus mlgh is going to equal, I'm going to factor the v squared out of these two terms, and I'll have v squared times 1/2 ml plus 1/2 mh. And then I would divide both sides by this. And so I would get, let's see, can I do any factoring out here? GH is common to both terms. So I can have MH minus ML times GH. And on the bottom, I'll have 1/2 ML plus 1/2 MH, which this actually ends up being the average mass, or the average of the two masses. Not that that matters a whole lot, but that'll be, whoops, it's not V2, it's V squared. So then V, when it hits the floor, is going to equal the square root of all that stuff. MH minus ML GH, and on the bottom, 1/2 ML plus 1/2 MH. And I guess I could multiply top and bottom by 2 and get something like that anyway. But there's my expression for the speed with which the bucket strikes the floor. And let's see what we get. Let's see, that was MH, not M4. Okay, well, MH minus ML is going to be 4.0 kilograms. And I just did the subtraction in my head, times 9.81 meters per second squared, times h, which is 2.00 meters. And on the bottom, I think I can do that one in my head. It's actually 1/2 the sum of ml and mh. So 8 and 12 is 20. 1/2 of that is 10.0 kilograms. And so I would get that. Now the kilograms will divide out. Kilograms here, kilograms there. Meters per second squared times meters are meters squared per second squared. But I'm taking the square root and I'll get meters per second. So that will work. Let's just plug in the numbers and see what we get. I had a syntax error. For some reason, I put in a parenthesis, which I didn't need. Okay, I get 2.80 meters per second for the speed at which that bucket strikes the floor. So I was able to do that. Now, in the Atwood's machine lab that we did, we found that the acceleration, or an expression that we used, was that the acceleration was equal to m2g minus m1g divided by m2 plus m1. And we had to do a bunch of work to figure that out, but let's see if we could get it here and what we might do with that. Now, this is a constant acceleration situation where we didn't time it or anything, but what you can do in those equations, you can, or situations, you can get v squared is equal to v naught squared plus 2a. In this case, I could call it the distance it moves through. It's usually delta x or delta y, but we'll just call it h here. And v naught is equal to 0 because you release it from rest. So the acceleration here ends up being v squared over 2h. Okay, well, can I do anything with that? Yes, I can, I think. If I multiply I'm going to go back to one of my early equations on this thing, like this one. Yeah, that'll work. Rearrange terms. I've got mhg minus mlg. In this equation, I'm factoring out the h. Times h is going to equal v squared times 1/2 times ml plus mh. Now, if I divide both sides by h, on the left side, I'll have mhg minus mlg. On this side, I'll have v squared. That 1/2 times v squared I can put down here, and I'm dividing by h. I get that, ml plus mh. And I divide by that, and I'll have v squared over 2h, which is the acceleration, is going to equal mhg minus mlg divided by ml plus mh. And that's the exact same expression for acceleration that we had, except that I called mh, or m2 was the heavier mass, m1 was the lighter mass, and I called them mh and ml. But it's the same expression. So you can get often the same expressions by using energy conservation methods or by using Newton's laws and going through things. And these aren't the only two ways to get things. There are other formulations that are actually a whole lot more complex than either one of these. There's Lagrangian mechanics and Hamiltonian mechanics, various things that can be applied to much more complex situations, and they'll simplify things. But Newton's laws aren't the only way to do things. They just happen to be one of the more elementary methods. So they work out pretty well. Okay, I want to start consideration of a type of force that isn't constant. And we've been dealing with the gravitational potential energy as if the gravitational force is constant. And if you stay close to the surface of the Earth, it is pretty much constant. But if you start moving far away from the Earth, then things change because the gravitational force actually gets weaker with distance from the center of the Earth. But we're not going to go that direction. Instead, the variable force we're going to look at is called a Hooke's law force. And the typical Hooke's law force is something where you've got a spring attached to something, and you can attach it to a mass, and we'll imagine that the mass can move along a frictionless surface, so it does something like that. But a Hooke's law force, a spring force, is such that there's an equilibrium length for the spring, where if you just let it be to itself, it'll assume some particular length, and we call that the equilibrium length. If you try to stretch it from that equilibrium position, the more you stretch it, the harder it gets to stretch it. Or if you try to compress it from that equilibrium length, the more you compress it, the harder it is to compress it. Now, as far as compressing it, you have to assume that the coils have space between them to start with. And you can get some springs where their equilibrium position actually has the coils touching each other. Okay, so it's already pretty much fully compressed. And if you try to compress it from there, it doesn't compress very well. But if you have a spring that's kind of stretched out like this in its equilibrium length, then you can compress it or stretch it, and you find this to be the case. And Hooke found that the force exerted by a spring in that case is the negative of a proportionality constant that depends on the spring that you're dealing with times the amount of stretch that you give it, which would be x minus, whoops, it's supposed to be minus x sub e, where x sub e is its equilibrium length. And so this is the amount of stretch or compression that you're giving the spring. The minus sign means that if you try to extend the spring, it will pull back. And if you try to compress the spring, it'll push back. So if you make x greater than x sub e, you're stretching the spring. And so this part's positive, but then the force is negative. Okay, so anytime you pull it to the right, it's going to pull back. If you make x less than x sub e, x minus x sub e will be negative, and you'll have a negative times a negative. The force will be in the positive direction. So those are some things about forces that vary with position. Now, it may seem like this can't possibly be very useful, although if you were a car designer that was, say, designing or selecting springs for a car as part of the shock absorbing system, you might be concerned about things like this, and a lot of that stuff shows up. There's industrial applications that are similar, but it turns out it's at a lot of different levels, different forces can behave like a Hooke's law force. And one of the situations is if you happen to have a diatomic molecule, like suppose you've got two nitrogen atoms in a molecule. They're held together by what we call a chemical bond, but in this case, the chemical bond is the electric repulsion between the two things, but the nitrogen atoms will settle into a place where they've got an equilibrium balanced between the two. And if you try to separate those two atoms from that, the force of attraction will pull back. And if you try to compress them closer than that, it will push back. And so for very small displacements about their equilibrium situation, the two atoms in a nitrogen molecule, which by the way make up 78% of the Earth's atmosphere, they'll behave as if there's a spring between them. And that spring will kind of behave as a Hooke's law spring, and to a pretty good approximation, actually. And there are a lot of different diatomic molecules that show up. It doesn't have to be two of the same thing. You could have a carbon monoxide molecule, just a C and an O, and the force between those behaves this way as well. Now, in this class, we're not going to study something that can happen as a result of this, which is an oscillation, where if you like push this mass in and let go of it, the mass will end up bouncing back and forth through an equilibrium position or oscillating back and forth. Same with the nitrogen molecule. You can get the two atoms in the nitrogen molecule doing something like this, moving back and forth. And the molecule will give off some electromagnetic radiation that's a characteristic of that particular mode or that particular vibration. And we can look for that out in space, say, if we're trying to find nitrogen in space. You can find all sorts of different things with this. But anyway, that's Hooke's law. Now, how do you figure out the work when a force behaves differently with position? Well, here's how we'll do it. We'll pretend that we're doing the work against the force, the spring force. And so we'll imagine that we have to exert a force as we stretch the spring. And you could think of we can define the equilibrium position of the thing to be 0. And we'll just have x sub b is equal to 0. But what we see here is the force the spring exerts is proportional to the amount of stretch beyond that thing. Well, the force that we would have to exert to stretch the spring would just be the same thing with a plus sign. And so what we will get is we'll have to exert a steadily increasing force. This force might be measured in newtons. This stretch might be expressed in meters or centimeters or who knows, whatever. But the equation of this line ends up being F equals kx. Okay. Well, how much work do we have to do to stretch something by some particular amount? Well, we could figure out the amount of work that we have to do for some tiny little incremental stretch, and then where the spring force is relatively constant, we just have a tiny little delta x, and in that we'll have an approximately constant spring force. But if we did that, we'd add up a whole bunch of those things, and what we'd end up with is the area of this thing, as we can call this x final. That's where we end up stopping it. Well, it's the area of a triangle is what it is. It's not really an area because it represents work in this case, but the height of this thing is going to be kx final, and the area of a triangle, which is going to be the work that we would have to do against that thing. So the work by us is going to equal the area of the triangle. Is going to equal, it's 1/2 the base, which is the base has a x final, times the height, which is kx final. And what we get is that the work that we have to do against a spring to stretch it from its equilibrium position out to some final position is going to end up being 1/2 kx final squared. Okay, and that will be the work we do against the spring, but it's equal to the work that is now stored in the spring. And so that's kind of neat. That's going to let us do some things with spring forces. Now, before we actually go on and solve one, I want to show you what you would have to do if the spring was already stretched by some amount beyond its equilibrium position. So we'd have a, whoops, this is supposed to be a force here in newtons somehow. Oh, by the way, this K here is something called the spring constant. And it has units of typically newtons per meter. And it tells you how many more newtons you have to exert every time you stretch it by an additional meter. It could also be written in newtons per centimeter. We do a lab at school where we figure out the spring constant, and we use centimeters for our measurement of stretch. And that's one that you could also use there. But what if we would have our sample, this is the force we would have to do against the spring, but instead of going from 0 out to some position, we're going to go from some x initial to some x final that's out here. Well, it turns out we want the area under this whole thing again, and instead of being a triangle this time, it's a trapezoid. It's a rectangle with a triangle stacked on top of it, but it turns out, in this case, we'd have F equals kx again. Turns out the work that we would do in stretching it from x initial to x final ends up being 1/2 kx final squared minus 1/2 kx initial squared. Now, the 1/2 kx initial squared would be, I could make dots here. This part is going to be this little triangle here. This part would be this entire big triangle here. So all we did was just take the big triangle, which would be going from 0 to x final, and subtract off the part that we'd have to do to go from 0 to x initial. So it would be the giant triangle minus the smaller triangle inside, and that would give us the area of this. And so it kind of makes sense that that's the case in this for starting with an initial stretch. All right, well, let's try one of the sample problems I stuck over here. These are on the handout that I posted here for today. We have a string that's fixed at, or a spring fixed at one end, compressed from its relaxed position by a distance of 0.20 meters. Okay, this time we're compressing the spring, but it turns out energy is stored in a spring when you compress it, and it's still given by the same expression. The graph shows the applied external force F sub x versus the position x of the spring, and find the work done by the external force in compressing the spring 0.20 meters starting from its compressed position. In other words, we just want the area that's under here. Okay. Well, we don't know what the spring constant is yet, but we can actually calculate the area without even knowing that. Oh, let's see. Yeah, okay. So for part A, we want to know this total area here. Well, that area is going to equal 1/2 kx squared. We could figure out k, but they don't have us do that. Or we can just calculate the area. So for part A, the work is just going to be 1/2 the base times the height. Well, the base is 0.20 meters. The height is 15 newtons. And I've been rattling off this area of a triangle thing. Area of a triangle is 1/2 base times height. So that's what I've been thinking here. So anyway, 1/2 times 0.20 is 0.10. 0.10 times 15 is 1.5. So this would end up being 1.5 Newton meters, but a Newton meter is a joule, so 1.5 joules is what I'd have there. I'm going to add a part C to this thing. And that's going to be what is K, the spring constant, okay, which we can figure out. Where are we? For part B, find the work done by the external force to compress the spring from 0.10 meters to 0.20 meters. Well, we could just go ahead and find the area of this trapezoid that's here, which that'd be the area of this thing. But we can, and actually it's that formula that I gave you. The work is going to be, oh, it's the total triangle area minus the little triangle area. Well, I figured out the total triangle area, which is 1/2 times 0.20 meters times 15 meters. And if I subtract away the little triangle area, that's going to be 1/2 times the base is 0.10 meters. The height is, let's see, that one gets all the way up to 15. I bet this is 7.5 if I went over here and figured it out. So that's going to be 7.5. Whoops, this is newtons. Okay. And so that's a way that I can figure this out just from geometry, just from area equals 1/2 base times height. And, oh, let's see. I don't feel like doing all that in my head. That was 1.5 joules. This is probably going to be a lot less, like 0.375 joules, I think. But let's check it out. 0.5 times 0.10 times 7.5. Turn on calculator first. Yeah, it's 0.375. So this one was 1.5 joules minus 0.375 joules. And meter times a newton is a newton, meter is a joule, and got all that stuff. Let's see. I can't keep that many significant figures, but if you could, it would be 1.125 joules. Really, you'd have to round that down to 1.1 joules, but this is a nice straight line here, so we can read these things more precisely than what they're showing. Okay, what's K? Well, here's something I know, and that is that for this initial situation, that 1.5 joules is going to equal 1/2 K times x squared. And the x in this case is the 0.20 meters. So I can do that. In fact, it might be easier if I just left it that way, but I'll just go ahead and do it. So K is going to be, multiply both sides by 2 times 1.5 joules, and divide by the x squared, which is 0.20 meters squared. And I will get, it'll be newtons per meter. Actually, yeah, if I think of this as, instead of a joule, as a newton meter, then a newton meter divided by a meter squared is going to be a newton per meter. And I'll get 3 divided by 0.2x squared is 75 newtons per meter. That's the spring constant for the particular one that we're dealing with here. So that was an additional question that I tagged on there. But anyway, tomorrow we'll do some more problems with springs. There's an example problem in your book. I forgot which number it is, but it turns out there's an atomic force microscope can be used to measure forces between atoms or molecules at the nanometer scale. And you're experimenting to find the elasticity of biological membranes by poking the probe into things. This sounds like torture to me, but maybe not. Anyway, we'll take a look at that one tomorrow. Let's see. I wanted to mention today is technically the last day to drop a class, but it's the last day to drop a class with instructor permission or without instructor permission. And because we just had our second test last week and I still have some work to do on that, or work to do on your first retake, and I also am going to let you do a retake on this one, turn in solutions to it. But I'll sign you out of the class if you decide to withdraw as late as next Monday. And so between now and next Monday, I want to get your retake of the first test graded. And then I'll also have you do a retake on this second test, and it'll be due by Friday night. And so retake.
Have you finished grading test 2?
Yeah, and I'll be emailing those out as soon as we're done here.
Okay.
At 11:59. So anyway, we'll do that. And so then by next Monday, you'll have a very good estimate based on your test scores. Tests are 60% of your grade in the class. Keep in mind, though, you do not get to do a retake on the final. So if you really don't do well on your first go round with tests, you may want to think hard about that. So, but anyway, by next Monday, you'll have a very good idea of your test performances. And so you can estimate a grade for yourself. I think that's better than having me provide you with it. And you can make that decision. And I will give you, I think I have to send something over to the registrar saying so-and-so has permission to withdraw from the class. But I can do that by next week.
I have a question about the sapling homework.
Okay.
So, I think the first 6 questions we've already covered with like work and spring and the law of conservation of energy. But then after that, there's stuff on power consumption, I think centrifugal
I need to
energy.
extend that.
Yeah.
Yeah. When's it due, or was it due already?
I think it's due on Thursday.
Oh, this Thursday?
Yeah.
Oh, okay. Yeah, we'll probably be doing power on Wednesday. So we may.
Tomorrow's, I think, Wednesday, though.
Oh, let's see. Tomorrow's Wednesday. Yeah, I might have to postpone that till Friday or Saturday. So, yeah, thanks for pointing that out. Yeah, but we'll be able to get that done anyway. Okay, I think I'll stop here and start emailing tests to you all. So do that, and then I can eat lunch.